Now we want to look at solving a linear system with 3 equations and 3 variables. So you can see the general form of that. So we're going to have 3 different variables, and there are 3 different types of solutions that you can get from these. You can get a unique solution, which is that all 3 of these planes, because they're 3-dimensional, cross at a single ordered triple, x, y, z. You can also get infinitely many solutions, which would mean that all 3 of these planes cross on a line and that every point on that line is a solution. And then there are a couple different ways where you can get no solution. Notice in the first image here, there are some crossing points of some of the planes, but all 3 of them do not cross. So that it would still be a no solution. And then of course that last image is all 3 parallel planes. They don't cross anywhere as well, so no solution there. So what we're going to use is what's called the Gauss-Jordan elimination method. So you're going to be performing operations, and basically it's operations that we already knew we could do. You're allowed to interchange any 2 equations, so you can just reorder your equations if you feel like it. Obviously, that doesn't change the meaning of anything. You can also replace an equation by a non-zero constant multiple of itself. So you can multiply an equation by a number. And you can replace an equation by the sum of that equation and the constant multiple of another equation. So basically, we're going to be doing an extended elimination version of solving on these. So I'm going to get us set up here. Now, the basic goal is to try to eliminate one of your variables so that you get back to a 2x2 system that you already know how to work with. So we've got to pick on one of the variables. And when I see this ordered, this set of 3 linear equations here, the first thing I always do is I take a look at the x's and the y's and the z's, and I try to pick out which one of those would be the easiest one to pick on, the easiest one to eliminate. None of these look like they would be terribly difficult, but to me, I think that the z's are the hands down easiest ones to do. Because we already have opposites. The first one is the opposite of the second one. So if I call this equation 1, 2, and 3, 1 and 2 are already opposites, a plus z and a minus z, and then 1 and 3 are also opposites, the plus z and the minus z. So the first thing I'm going to do is I'm just going to take equation 1 and 2 and add them together. No multiplication is needed here. I could do that if I needed to, but that's why I picked on the z's. I'm just trying to work smarter, not harder when I do that. Could you eliminate y's or could you eliminate x's? Of course you could. Just try to pick the lesser of the evils though. So whenever I add here, I get 3x minus y, the z's cancel, equaling 1. And I like to box that in when I get it because I'm going to need that later. Okay, then what you do, now we've got an equation with only x's and y's, so it's like, hey, I like that better. That's like something I already know how to work with. Then you want to do that again. So you have to eliminate the same variable again. You can't first eliminate z's and then all of a sudden pick on a different one. So I have to stick with z's. And you have to include the one equation that hasn't been used yet. So I haven't used equation 3 yet. I have to use equation 3 now with one of the other 2. And in this case, it's easiest to use it again with equation 1. So I'm going to go ahead and perform that addition. And then add that to the 3x plus 3y minus z equals 11. I know there's not a lot of room to work here, but let's see. That's 4x plus y equals 6. And now what you've created is a 2x2 system. So now we rewrite those 2 that we've created. And now our task is to solve this. You at this point can use either substitution or elimination whichever one you prefer. I think this is, again, a great one for elimination because the y's are already opposites of each other. So I'm going to pick on those. I don't need to do any multiplying. I can just add this together, cancel out those y's. We get 7x equals 7, so x is 1. Now I know x, so I've got x. I need to find y. So use one of these squared in equations that you've got here. One of these, you're basically back subbing back up to the top. So I don't want to go all the way up to one of these equations up here yet because I need two variables in order to find the last one. So I got to work my way back up. So my choices are either here or here. Pick one of those. I have x, I'm trying to find y. I think I'd prefer to use this one because the y, what I'm trying to find, is a positive coefficient. So I think I'm going to cause myself less worry if I do that. So 4 times 1 plus y equals 6. 4 plus y equals 6. So y must be 2. Okay, so it's like we've got x and y. We're not done though. We need to know all of them. So I need to now substitute the x's and the y's back into one of the equations, one of the original ones, in order to find z. So I've already predetermined that I would like to use equation 1. Again, why did I choose that? I'm solving for z. So it appears to me, in my own opinion, that the easiest way to solve for z would be to use the one that already has the positive coefficient. So that equation, just to remind us, that equation is x minus 2y plus z equals negative 5. We've found that x is 1, y is 2. So sub that in. 1 minus 4 plus z equals negative 5. Negative 3 plus z equals negative 5. It looks like z is negative 2. Your final answer for one of these is then, because this one has a solution, it has a unique solution, which is an ordered triple with those values. So it's the x value 1, the y value 2, the z value negative 2. And that's the gist, or the basic way that you solve a system of linear equations with 3 variables and with 3 equations and 3 variables.